Hey everyone, we're going to pick up in our chapter 14 slides. We just finished talking about dehydration reactions with alcohols, and so we're going to talk about another kind of reaction that alcohols undergo. This one is a little more in depth and can seem a little more complicated, so we're going to walk through it really slow with some practice problems. And please reach out to me with questions regarding these oxidation reactions if you just seem to not, if it's not clicking very well with you. But the first thing I want to do is, so I'll say the second type of reaction that alcohols undergo is oxidation reaction. So the first one was dehydration. The second one would be classified as oxidation. And I want to redefine what I mean by oxidation, because if you took 1402 recently, or even if it's been a while, that definition you got for oxidation reactions was an inorganic based definition. Where we view the oxidation of any atom or compound as losing electrons. Okay, and then the reduction of any atom or compound is any atom or compound that gains electrons. And so I know when I teach it, we go over oxidation numbers and how those change and identifying what's losing and gaining electrons. You might be familiar with the acronym oil rig. Oxidation is the loss of electrons and reduction is the gain of electrons. But for organic chemistry, although this is a type of oxidation and a type of reduction, we're going to think of it a little bit differently. So specifically in organic chemistry, we're going to think of oxidation as an increase in the number of carbon-oxygen bonds. So you're going to be always counting how many carbon-oxygen bonds you have kind of from here on out. An increase in the number of carbon-oxygen bonds and or a decrease in the number of carbon-hydrogen bonds. So I like to give this example. A carbon-oxygen single bond, a carbon-oxygen single bond becoming a carbon-oxygen double bond. Here you're going from one carbon-oxygen bond to two carbon-oxygen bonds. Okay, a carbon-oxygen single bond represents one carbon-oxygen bond. A carbon-oxygen double bond right here represents two carbon-oxygen bonds. So if we're increasing the number of carbon-oxygen bonds, we'd say, well, this molecule, whatever it is, has been oxidized. All right, and then reduction is just the opposite of that, decreasing the number of carbon-oxygen bonds and or increasing the number of carbon-hydrogen bonds. So these are the types of definitions we're going to use to think about oxidation reduction. And we will be assessing this with pretty much all the functional groups we have from here on out. So in your homework questions in class on the exam, there's all different kinds of oxidizing agents. So you might see some sort of reactant molecule. And then it might have, on your homework, it might have KMNO4. If it has something like this, what you should infer is, if the problem doesn't tell you, you should infer, okay, this is an oxidation reaction because I recognize this as an oxidizing agent, or I recognize this as an oxidizing agent. On the exam, you'll see me do things like this, where I say O here representing your oxidizing agent. And so I'm telling you, if I give you a reaction like this and I want you to say, I want you to draw the product or something, I want you to understand what's happening is that this compound X, whatever your reactant is supposed to be oxidized, and you should draw the product of that oxidation. So if you have any questions about how that looks on homework questions, just reach out. But so speaking of alcohols, here is our alcohol product. You see the OH group bonded to this carbon, and we don't know what kind of carbon it is. We'll talk more about that in a second. Here you see this little O, like I was talking about, indicating some sort of oxidation is going to happen. And then we can recognize that we're going from a carbon-oxygen single bond here to a carbon-oxygen double bond. And because we're increasing the number of carbon-oxygen bonds, this is oxidation, right? Now the way this happens with the hydrogens and where this double bond comes in is kind of noted over here. It says two hydrogens are removed from the alcohol. One hydrogen is pulled off the OH group, one hydrogen from the carbon that is bonded to the OH group or bearing the OH group. So it's just these hydrogens in blue. We're going to pull these off, which is why you see H2 as another byproduct over here. And so there we have space on the carbon when we pull this hydrogen off to form a double bond to oxygen. Now, this is the generalized view of it. However, this gets pretty specific because you will get different products depending on what type of alcohol is reacting. So if you have a primary, secondary, or tertiary alcohol, the reaction goes different ways. So I do want to make sure for the exam that you could identify what kind of alcohol you have, primary, secondary, or tertiary, which we have already practiced doing, and then write the product based on your understanding of how that particular class of alcohol oxidizes. So what does it look like for primary alcohols? Why is this considered a primary alcohol? Orient yourself for a second if you don't remember how or why. It's because this carbon right here is only bonded to one other carbon. And so this R, I know this R doesn't look like a carbon, but this R is indicating some sort of carbon-carbon bond. Oftentimes when you see an R bonded into a molecule, it's representing some sort of other alkyl group, some sort of carbon bond. So we have one carbon-carbon bond, and specifically the carbon bonded to the OH group is bonded to one other carbon. That's what makes it primary. And when we oxidize this, our first stop, because you see there's two arrows here, this can go a step further, but our first stop is that we're going to form an aldehyde. Okay, so how does that happen? Come back here. Remember, we're going to take this hydrogen and this hydrogen off, and then we're just going to be forming a double bond between the carbon and oxygen, okay? So that's literally all we have. This green hydrogen at the bottom kind of just swings up and is oriented to the right here in our aldehyde, but we've not added any new green hydrogens. We've just moved that bond around. The carbon maintains 4 bonds at every stage. Make sure when you draw your products that your carbons always have 4 bonds. But if you recognize this functional group, we haven't really dived into this, and it's been a while since we mentioned this, but this right here is an aldehyde. It's a carbon-no-carbon with a hydrogen bonded to it. So because we can continue this reaction even further, which is what we're going to talk about next, we separate these oxidations, and we would say this would be mild oxidation. So if you read a problem on your homework on the exam that says, mild oxidation is occurring or under mild oxidation, then you would want to just draw the product as an aldehyde. However, since we can continue oxidizing it, we would consider this strong oxidation. Okay, so if you read a problem that says you got a primary alcohol, or it shows you a picture of a primary alcohol, and the arrow says strong oxidation, or the problem somewhere indicates strong oxidation of the primary alcohol, then it goes all the way to a carboxylic acid. So what happens if we look at this aldehyde is this hydrogen comes off, and instead it becomes an OH group. And we are going from 2 carbon-oxygen bonds here to a total of 3 carbon-oxygen bonds, right? Because we've got the 2 to the oxygen up top, and then another carbon-oxygen bond there, so a total of 3. So remember, an increase in the number of carbon-oxygen bonds represents oxidation. All right, so that's primary alcohols. Secondary alcohols, they can only be oxidized one way, and again, what we're doing is we're taking these hydrogens off. Okay, and when we do that, we're going to form the double bond to the oxygen. Remember, this is considered secondary alcohol because now we are seeing 2 bonds from that hydroxyl-bearing carbon to 2 other carbons represented by these R's here. And so anyways, back to the hydrogens and removing these. This R, by the way, you see this little prime symbol on it. This is the same R here. They swing this up to the right. We're not adding any new R's. But we take these hydrogens off and we form the double bond to oxygen. And so if you recognize now, and it tells you beneath that our product is a ketone. So remember that a carbon, no carbon, that is double bond to an oxygen, when it has 2 other carbon bonds on either side, we call that a ketone. What does our note say over here? Oxidation of secondary alcohols produces ketones. No further oxidation takes place, unlike primary alcohols. And then this is pretty simple. Tertiary alcohols, because we have no, if you look at this carbon, it's a tertiary carbon. Because there's no hydrogens to pull off, they don't oxidize. All right, and that's what is being explained over here. No oxidation occurs, so you would just write no reaction, no change, no product, something like that. So make sure you understand the most difficult one is that primary alcohol. Mild oxidation produces an aldehyde. Strong oxidation produces a carboxylic acid. Secondary alcohol, the only kind of oxidation you can get is going to produce a ketone. And then tertiary alcohols do not oxidize. So let's do a little practice. This problem is having you work backwards. It says, from what alcohols might the following products have been made? So you want to look at the compound as it's drawn out and think, what kind of alcohol would have produced that? So it's pretty easy if you just remember, I'll highlight them in pink, what kind of product you're getting, okay? If what is shown in this problem is an aldehyde or a carboxylic acid, then you know your initial alcohol was a primary alcohol. And if what you're seeing is a ketone, then you know it was a secondary alcohol, and it wants you to draw that as well. So instead of just telling me what kind of alcohol, draw it as well. So if you look at one here, I would pause the video and actually try to work ahead of me and then come check yourself. But I'm going to go ahead with it. We have a ketone is what we see for number one. That's the product. So obviously the type of alcohol that produced this would be a secondary alcohol. So we need to now draw a secondary alcohol. So what I'm not going to change is anything that I'm going to highlight in pink. This should all stay the same, okay? None of those bonds are ever tampered with. What should change is what I'll highlight in blue, okay? This carbon-oxygen double bond should be broken down to a carbon-oxygen single bond, and the O should become an OH group, okay? Rewatch that if you missed what I just said. So I'm going to continue to just draw my CH3, CH3. I'm also going to move this down for space purposes and shrink it up. Okay, so this is going to become a single bond, right? And the O that was double bonded is actually should be an alcohol, right? It's a secondary alcohol, so it's got to have an OH group on it somewhere, and there it is. But now if you look at this carbon, the one I'm highlighting in gray here, we only have 3 bonds on it. So what else do we need to add? Well, remember, we're always pulling a hydrogen off right here, off that carbon, that hydroxyl-bearing carbon. So we need to put a hydrogen back on it since we're undoing this or drawing the type of alcohol that produced this ketone. So this should be the alcohol that produced our ketone product. Okay, let's do number 2. If you're looking at number 2, here's the functional group. There's a carbon-oxygen bond there, and this carbon is bonded to a carbon there and a carbon there. And that's all 4 bonds. Nothing else missing on that carbon. So this is definitely a ketone as well, which means the type of alcohol that produced it was also a secondary alcohol. So if we try to draw that, again, I'll highlight in pink, the part that does not change is going to be all of this. This should stay the same. The part that should change is what I'll highlight in blue. This right here should change. So let's just draw our, what is that? 1, 2, 3, 4, 5, 6, 7. Cycloheptane type structure. That's hard. Getting 7. I'm already bad at hexagons, so this is going to be unique. Okay. I think I got 7. 1, 2, 3, 4, 5, 6, 7. Yeah. This should stay the same. None of that changes. But now I'm going to make the carbon, what was a carbon-oxygen. Wow, that's a long bond. That's also a long bond, but whatever. Put my oxygen there. It should now be a single bond, and it should become an OH group. And then this, if you're drawing just the line structure, you're done at this point. But remember that we're also putting a hydrogen back on this carbon, because if you look at this carbon highlighted in gray now, we only have 3 bonds on it. But if you understand from line structure that there is one hydrogen that gets added back on, then you just understand, okay, there's actually 4. But if it helps you, just draw that hydrogen out. So that would be the alcohol that produced the ketone in problem 2. Lastly, number 3, you want to identify what kind of functional group do we have in this product. We'll highlight it. Well, we'll highlight it a different color. I'm going to highlight it in orange, if you can even see orange. But it's right here. Hopefully you already noticed it. What functional group is this? You might want to go look at the slides above if you're not sure. If you need to pause this video, do so. This is a carboxylic acid. So the type of alcohol that could produce a carboxylic acid would be a primary alcohol when it undergoes strong oxidation. So we need to draw a primary alcohol. So I'm going to, the part of the molecule, again, that stays the same would be all of this. That should all stay the same. What should change is honestly what's highlighted in orange. So let's just draw everything the same. You can draw in line structure if you want. That's actually what I'm going to do. There's a CH3. Whoops. And then we have the CH2. And then, okay, now we're at the carbon that is going to be bonded to an OH here. And then we're just going to put on 2 hydrogens. There and there. Now, if you're just doing the line structure, then you don't have to draw those hydrogens in. You could just make it look like this. Okay, but that's a primary alcohol. Okay, so remember, if you're like really confused right now, the carbon we're really focusing on, I should highlight it a different color, is this carbon right here. And to make this a primary alcohol, this OH group gets entirely pulled off, and we're putting 2 hydrogens back on this carbon highlighted in blue, plus this bond right here, this carbon-oxygen double bond, should become a single bond, and it becomes an OH group. So it just will help you if you come back up here and look at this. To form a carboxylic acid, which is all the way down here at the end, we're trying to redraw the primary alcohol. Okay, so if we look at this primary alcohol that is in my box right here, both these hydrogens in green and blue end up getting removed to form the carboxylic acid. One at a time, but they both get removed. So that's why what I just drew down in our practice problem, I put 2 hydrogens back on that carbon. And then you got to have the OH group as well. Okay, so this top O, double bonded O, gets turned back into the OH group, and then this gets ripped off and you put 2 hydrogens back on. Okay, if you have any questions on this, email me, reach out, but please make sure you watch this and understand this before Friday, because we'll pick up with phenols in our next lecture.